Dr. T.V. Geeta, Professor, Department of Computer Science, College of Engineering, Guindy, Anna University. Her special interest, Artificial Intelligence and Natural Language. She has published more than 143 articles in national and international journals. She has guided around 7 PhD students. She has got Young Scientist Award from Government of Tamil Nadu in the year 2000, Chief Minister's Special Mention Award in the year 2002, and Woman of Excellence by Rotary Club in the year 2003.
Good morning to all of you. Today we are going to talk about stacks. Stacks is just as you have seen about lists, we are going to talk about stacks. Stacks is a very important data structures and is necessary for implementing the logic behind many programs. So let us look at stacks. At the end of this lesson, the objective of this lesson is to introduce you to the concept of stacks, and then to look at all the operations of stacks, and then the applications of stacks. So these are the things that we are going to talk about in this lesson. So before we go on to the computer aspect of stacks, as you know, there are stacks every day in our life, like a stack of shirts, a stack of books, and a stack of boxes, and so on, as you see. Now the idea is that normally when you take out the first shirt you take out, it will be the top shirt of the stack, and so on. So these are otherwise the rest of it will fall down unless you catch it very carefully. So the same concept is applied to stacks in data structures. So this is a typical application of stack, where you have a stack of books and a stack of coins. The same thing is represented in a computer stack. A computer stack has got a number of objects that are placed one on top of the other in a sense. So another common linear structure, data structure, that I already talked to you about is stack. One we have already seen is the list, and in a way the stack is nothing but the list, but there are a lot of restrictions on how the list is used, then it becomes a stack. With the stack we have restricted the access to the list to one end, and we take out elements from the stack using the pop element, and we push elements into the stack using push operations. So the result of this restriction is that the list pile one on top of the other. So basically when we talk about stacks, we talk about what is called the last in first out policy. To get the bottom item, we must first remove all the items above it, in other words. So the behavior is sometimes described as, and this is the policy that we talk about, which is called as last in first out. So whenever you think of stacks, you must think of it as a last in first out. Whatever you put in last will be taken out first, or it's also called as LIFO, and this is because, as I already told you, the last item put in the stack is the item that is removed first. So elements can be removed and added only at one end, and this end we call as the top of the stack. With the stack, the top item is always the last item to enter the stack. It is always the first item to leave the stack, because no other items can be removed or added onto the stack without affecting the top element. So let's look at some terminologies about the stack. So the depth of a stack is the number of elements it contains. So suppose you have 10 elements in the stack, it's deep 10, and you say that the depth of the stack is 10, and normally, as obviously, an empty stack has got a depth of 0. So why do we use stacks? So stacks provide a very efficient storage structure for manipulating data that is accessed according to its policy, that is the last in first out policy, and stacks are often used as temporary storage to facilitate the solution of a problem. So stacks are restricted linear lists, as I already told you, where additions and deletions are made only to the top, and what happens is, because of this specialization or restriction that we do on the stacks, we can implement the stacks using linked list, and we can also implement the stack using arrays, and we can think of ways in which the efficiency of the implementation can be improved. So as before, we have just seen basically what a stack data structure is. Stack data, you must remember that a stack data structure is a restricted type of list, and it follows the last in first out policy. All access to the stack is through the pointer called top, and through the top you can insert elements and delete elements, and the last item which has been inserted is the first item that is to be removed. Now let us look at all the operations that you can do on stacks. So first operation that we do on a stack is what is called a max item. Max, that is nothing but the maximum number of items that would be on a stack. Now, before we go into details about this, what the meaning of max item depends on the implementation of the stack. So, if it is a array implementation, we have already discussed array implementation, there will be a maximum size of the array, and that will be the maximum number of elements you can put in the stack. But how many elements has actually been put is the max items, and the item type can vary. It can be a single simple integer, or it can be a structure, and it can be, as we saw in list, it can be any data item. The others are make empty, that is an operation, that means make a stack completely empty, and you can also have a boolean operation called isEmpty, that is to test whether the stack is empty or not. Similarly, you can have boolean isFull to test whether the stack is full. This actually makes sense only when we are talking about array implementation. And next you have push x comma x. This is to add push an element to the top of a stack, yes, and then the function for this is that it adds x to the top of the stack, and the precondition is that in order to push an element into the stack should not be full, and the post condition is after the push operation, the element x becomes the top element of the stack. Next you have pop, yes, pop is nothing but operation to delete an element from the stack, and it is called pop the topmost element from the stack, and the function obviously is to remove the element from the stack and return the item. And the precondition has for any deletion operation for that matter, the stack should not be empty. It has to be initialized, and it cannot be empty. If it is empty, the pop operation becomes undefined. The post condition is that the top element would have been removed from the stack, and a copy of the item will be available, and the top has been modified. Then you have something called top s. This top s, as it is written here, is to access the topmost element of the stack. Here no change occurs to the stack, and only the topmost element, you will get the value of the element, that is it. So, let us go a little more in detail about the operations of the stack. So, you have first the push is add an item, and the problem here is that you can have overflow. Suppose you say that the stack can contain 10 items, and it's already full with 10 items, and you try to add another element, 11th element, then the stack overflow condition occurs, but this is only for the array implementation. And for the pop element, you remove an element, you can have, as I already told you can have an underflow, and the stack top is what's on top of the stack. So, this is a push operation where you enter elements, and this is a stack or pop operation where you take out it. So, let us take this in more in detail. So, you have a data that you want to push on the stack. Now, this is the initial state of the stack. So, for example, the stack has 2 elements, and assuming that the stack starts with top is equal to 1, here you have top is equal to 2. So, now when you say push, what happens is the element data is pushed on to here like this, and the top increments by 1, and the elements the stack size increases. Now, let us assume we want to explain the pop operation. As you already know, it removes a data element from the top of the stack. So, initially the stack has 3 elements, and top now points to 3. When you do a pop operation, there is no question of which element to delete, because you can only delete the topmost element. That is the way the stack is defined. So, what you do when you give a pop operation, the topmost element is deleted, and that is returned, and the top reduces by 1. So, this is the pop operation. Then look at this operation. This is a stack top operation, where before and after the top operation you do not have any change in the stack. Stack has 3 elements here, it has also 3 elements here. The top value here is 3, and the top value here is 3, and only thing is you are able to access this element, and the value is given out. Please note, when I say top is equal to 1, 2, 3, I am assuming it is an array and the stack which is stored in an array, and the top starts from 1. It is not necessary, you can start a stack from 100, you can array location 100, and you can also store stack in linked list. Then the meaning of this is different, but here we are explaining it so that you understand what the operation is. So, let us look at a simple figure here. If you look here, in the step 1 you have this empty stack, and you are given a data that you want to push on the stack. Now, what happens here, you will note that the top is equal to 0, and the stack is empty. Now, you have incremented the top by 1, and you are pushing in green into the stack. Now, this is the new position, a new value, the new condition the stack is in. Then With that you add another element which is blue here. So now top becomes 2 and blue is pushed onto the stack. This is the condition of the stack after the second push operation. Then what you do, we are going to see the pop. Now given this state of the stack, if I just give pop, there is no question of which element to pop because you can only pop the topmost element. So what happens after the pop operation, blue comes out and this is the new condition of the stack where top has been decremented by 1 and blue is no longer present in the stack. Then next let us see if you want to add another element, that element is pushed. This is similar to what we did here and top increments by 1. Then we are doing a stack top operation. Here what happens, the state of the stack before and after the operation is the same, but only thing is that you can access that element. Then this operation and this operation are same, we have just removed an element, and here also we are doing a pop operation. You see here that this green has been removed, that is the topmost element from the stack has been removed and the stack is empty. Now if you give a pop operation, there is an error in the condition because the stack is empty. So let us look at the stack as an abstract data type. So that means we are not bothered about the implementation we are going to use in the stack. So basically for any stack, whatever the implementation, the following are the operations or functions that are associated with the stack. So one is create, this means you just create an empty stack for the implementation. Then push, we have seen enough about push. Push means add an element to the top of the stack. Then you have pop, which means pop an element from the top of the stack. You do not have to specify the element because the only thing that you can pop from a stack is the top element. Then stack top, which we have already defined, that is you are accessing the top element of the stack, no change in the stack, that is the top remains the same and the number of elements in the stack remain the same. Then you can also have a full condition. The question mark that we have put here is you cannot check a full condition when you are doing a linked list implementation of a stack because you can keep on adding nodes dynamically to the stack, or the elements of the stack can be increased dynamically, but full makes sense when the stack is implemented as an array. And then empty is when the stack is empty, that is it does not contain any element. So this is the stack and empty condition. So we can just look at a small data structure of this. So you have a external interface, you can have a data structure and you can have the data here. So this is the data that you want to input into the stack. So this is just to give you a feeling of what is available outside. The outside is when you are when you are doing push, you have to indicate which element it is X to be implemented and which stack you want to put it. And similarly when you are externally defining the stack, you have to also know the access point, that is the top of the stack. So one typical application of a stack is the famous parenthesis matching or matching of brackets. So what you do here is you do not have a matching parenthesis here. So what you do is you input when you see, so you traverse the list from this corner. When you see a bracket, you put it in the stack. Then you see another bracket, put it in the stack. Then you see an A, just pass it, do not do anything. You see a plus, do not do anything. You see a plus B, you do not do anything. Then you see the closing bracket. So you look at the stack and see whether whatever you have on top of the stack matches this. If it matches, you remove that. So now you are left with this one bracket, the one that we put here. Then you see a divide sign, do not do anything, just pass it. C, you do not do anything. Then you have finished, you have come to the end of the expression. Now when you come to the end of the expression, if it was a matching expression, you should have had the stack as empty. Unfortunately now the stack contains a single bracket, so you know that the equation has not, the brackets have not been matched. Now if you look at the same thing, you can do it yourself and see, you will see that this you will put on the stack, there are no, then here you will put on the stack, here you will put on the stack, again you are left with a closing bracket that is not matched. So here you are matching, you are putting this on the stack, then you are putting the opening parenthesis on the stack, then you have a matching closing parenthesis which will cancel each other, but you are left with an open parenthesis. Here you will be left with a closing parenthesis, but however you do that, always you should have the stack empty, then only it is matched. Now in this example, we have taken a simple example where there is only one type of bracket. You can have any type, you can have a square bracket, you can have a flower bracket, and check the corresponding matching. So you can actually do parenthesis matching automatically using a stack data structure for any type of complex expression. So, as we already saw, the stack ADT can have several implementation. Implementations may be different, but the implementation details have to be hidden and the interface functions have to be the same, and most application programs should not see any difference just because I am using an array implementation or I am using a stack implementation. So, let us first look at the stack implementation using an array. So, stack is stored as an array. When you store a stack as an array, immediately it means that the number of elements has to be allocated, that is how many elements the stack can hold. So, I can here conceptually look at the stack as we have done before. So, I have defined something called a stack array, and then I have something called a count, and I have something called the stack max. Stack max is the maximum number of elements that I can store in this physical array, and top tells me the top element. You can actually not have the count also, it does not matter, but stack array, stack max and top have to be defined if you want to define a stack using array. So, implementing stack using arrays, it is a simple implementation. The size of the stack must be determined when a stack object is declared. Space is wasted if you use less elements. Suppose you have a stack and you declare it to have 100 elements, and usually the stack is within 10 and 15, then you are wasting the space, and we cannot push more elements than the array can hold. So, this is a typical definition of a stack of integers in a array implementation. So, what we are doing here is we are declaring an array called stack array, and then this is the number of elements, a count, then stack max. This is equivalent to what we saw before. For this we are defining a structure. So, and this is the maximum element, and this top is the index of the top element. So, all of them are integers in this case. So, first step here is creating a stack. So, you will say that create a stack with maximum elements. Okay. So, if the stack is equal to null, check if stack is empty, you return a null. Otherwise, you are going to now you are going to allocate a head and initialize and allocate the stop. So, first what you do is you initialize the top of the stack to be -1 and count is equal to 0. Remember, this is a stack which is empty, so it does not have anything. So, you can define the top in many ways. In this implementation, they have initialized the stack to be -1 and the stack count to be equal to 0, that is same. And then stack max has been initialized to the maximum number of elements that you want the stack to hold, and the stack array, that is the array, the complete array is defined as allocate maximum elements into size of the element size. So, if stack array is equal to null, then that means free the stack, otherwise return null. So, what you have done here is you have created a stack which called stack array, which has top equal to -1, count equal to 0 and stack max equal to maximum number of elements. So, next let us look at the push operation. So, the push stack, you have, when you remember when I told you that when you have a push stack operation, you have two things that you have to define. One is the stack array, which is the array in which you want to push it into, and the next is the data element that you want to push. So, first for any push operation, in fact this is true for any insertion operation, you have to first check whether there is place to insert the element, in other words. So, for that we are doing a stack check, full stack check. So, here what you are doing is, if the count of the number of elements is equal to the maximum number of elements the stack can hold, then you are returning 0, that is it is overflow, and that means the number of elements in the stack is equal to the maximum number it can hold and you cannot add any more elements. Otherwise, when you come out of this, it means that you have place to hold the element. In that case, what you do is you increment the count. So, the number of elements in the stack increases by 1. You increment top by 1 because now you want to create a place pointed at to by top where you want to insert the element. And then what you do, you in the array at that position called top, you insert the element that you want to insert and you return 1. This is just to indicate that the push operation has been success. If it was already full, then you would have had return 0, which means that there is a problem, there is an error, and in this condition the error is an overflow. So this is how you do. Please note here we are first incrementing top to create a place, and then you are putting the element into that top position. So next let us look at pop operation. Again, as you know, in any deletion operation you should have something to delete. So in deletion operation you will get an underflow. The same is true for stack. So here what you do is you are given a stack and you are given a data output pointer. This is the data you are going to output, and you are given a stack. Actually you need not have this as an input parameter. You can just give the stack and you can delete from that. But here we want to get out what is on top of the stack. For that's why we are having this extra parameter. Some pop operation implementation do not look at this as a separate parameter inside the pop operation. One of the examples that we saw before, we did not have two parameters for the pop operation. So here what you do is, please remember this is an array implementation. So what you do is you first check whether the stack is empty. If it is empty, then you cannot do a deletion operation because you do not have anything to delete. So you get an underflow condition. Otherwise what you do is you have to take out the item at the top of the stack. So what you do is access the top element of the stack and take it out in the variable called data out pointer, and decrement the count by 1 because now the count of the number of elements has decreased, and you decrement top also by 1 because previously whatever top was pointing to is now empty. So and you do not want to access it, so you will decrement top and return 1 to indicate that it is a successful operation. This is the top operation. This function retrieves the data from the top of the stack without changing the stack. So again, as we already saw, precondition is stack is a pointer to the stack, and post returns 1 if success, 0 if underflow. So here what you do is you have the stack again, and this is the output pointer as we did in the pop operation. So if the count is greater than 0, okay, then only you can do this operation. If it is less than 0, you do not have a top to access at all because the stack is empty, you do not have an element. So if it is not 0, that means there is an element, greater than 0, there is an element. So you just take out that element, not take out, you just access that element. But remember, no top changes, nothing changes, the count does not decrease, nothing happens, only thing is you are accessing the top element. So here after this top operation, the stack remains the same as I have already told you, and you are returning 0. This return 0 is if you are not able to do this operation because of count being not greater than 0, which means that the stack is empty. This is a condition to check whether the stack is empty or not. So the precondition is stack is a pointer to the stack, and the post condition is it returns 1 if it is empty and 0 if there is data in the stack. So here what you do is again you input the stack, and you if the that is the structure stack, and if the count is equal to 0, that means it is an empty stack. You just you will return the value, that is true value. Similarly full, this function determines if a stack is full. So full is defined as heap full. Okay, let us leave that heap full for later. So pre stack is a pointer to a stack head node, post is returns 1 if heap or stack is full and 0 if heap has room. So what you do here is this is a full stack condition. Again you have the complete structure. Now here, because it is an array implementation, when do you know the stack is full? When the count is equal to the stack max. So if the count is equal to the maximum elements the stack can hold, then we know that the stack is full. So then you return the value true. Now growable array based stack, this is a slightly different version of what we are trying to say. In a push operation, when the array is full, instead of throwing an exception, we can replace the array with a larger one. How large should the new array be? Incremental strategy, increase the size by a constant c. Doubling strategy, double the size. What we mean by here is we do not usually know, you cannot predict how much the size of your stack will be. Now the problem here is that if you put the stack as say 1000 elements and you are using only 10 or 15 elements, you are wasting your memory resource. On the other hand, if you put 10 or 15 and you are going to have 20 or 30 elements, then you constantly will be getting a stack full condition. So one way of doing this is have a growable array stack. So what you do is if you get a stack full condition, at that point you reallocate a larger array and then put all these stack elements into that array. So this is not a very simple operation, this changing of elements from one array to the other, but assume that you can do that. There are two strategies of how the larger arrays allocate, how much it should be. So one thing you can do is, suppose your original stack size was 10 and you have a stack full condition, you can increase it by a constant c, say 5, and every time you get a stack full condition you keep increasing it by 5. Now please note, this depends on the application, purely on the application. Or you can have a doubling strategy. Initially you put 10 and again you can put 10, and then again when now you have a stack size of 20, again you can put 20 and so on. So this is just like predicting. So depending on the application you can do this. Now we go in for the next type of implementation. Plus please note, but when I said we are going for a global array, after the stack full condition in an array happens, and when you allocate a larger array, there is a lot of computational work needed to transfer from this array implementation to the next array implementation. So it's not a trivial operation. So it's not to say that global array is a solution to the problem of using arrays for stack operations. So next implementation is the linked list implementation. So here what you do is, you have to understand the concept of an abstract data type again. We have already seen this, and you need to understand nested implementation, and you need to see some applications of linked list. So every data of course structure course also talks about linked list implementation of stacks. So this is a typical linked list implementation of a stack. So here you see that this is the conceptual view. Here the conceptual view of whether you implement a stack using linked list or whether you implement a stack using arrays, the conceptual view is the same. But when you looked at this, now what you have here is, the bottommost element will have the link pointer to be equal to 0, and then you have the next element pointing to this element pointing to this element pointing to this, and count is the number of elements in the stack as before, and top is now giving the address of the topmost pointer. This link is giving the address of the next topmost, this is giving the address of the next topmost, and the bottommost elements, the address or the link will be equal to 0. This is the linked list implementation of the stack. Now let us look at the stack. There is no count, there is no top, this is before you create a stack. Now look here, you have incremented you are creating an empty stack. So what happens is, you have count equal to 0 and top pointing to null, but still the stack is empty. You have just created a situation where you can create a stack. Now let us look at a push operation. Now what happens is, count is 0, top is equal to null. Now what I am doing is, I am creating a node to put green. This is the same operations that we saw when we did linked list implementation of a stack. So what happens after this green, I have to change the address of this top from null to the address of this node, and this next here has to be null. So next is again a push operation. Now this has to be a new node has to be created, and please note that this new node will come here, because now this becomes the bottommost node, and the top has to point to the most recent node or the topmost node. So now what you have, you increment the count by 2, this top will point to the new node, and the next of the new node will point to the previous top. So this is what happens. When you do a pop operation, what happens is, the blue has to be removed. So now top will point to green again, and blue will be removed. Its blue will be entered here and blue will be removed from there. So if you want to destroy the stack, what you do is, you make the count 0 and if you do not have any pointer from top, address of top, immediately the stack will not be accessible at all. So you have destroyed the stack. So here you have two data structures that you are using, or two nodes that you are using. One is the stack head and other is the stack node. So the stack will have a count and a top, which is count is just an integer, and top which is a node pointer. This will have a data type, and there will be a link which is again a node pointer. This is similar to the structure that you used for lists, but here the operations are restricted, as I already told you. Again, this data type can be a single data type, or you can have a large record or whatever. So the key data structures or structures that you use in C are again a node with integer data and struct node which is an address, and you can also have the stack, and the stack is represented by a count and the stack node pointing to the top. What I want you to do now is that let us try out some problems. First you try to explain any two applications of stacks taken from computer science, okay. That is what I want you to first do. Then you use a stack represented as an array to check the parentheses of expressions. Please note the expression that is given to you may have three types of parentheses, round brackets, square brackets and flower brackets. So, you have to match the corresponding parentheses and see whether the parentheses are correct in the expression. So, this stack is a typical data structure you would use for this. So, please try to do this. Now, in this lecture what we have done is we have spoken about stacks and some of its applications as well as how stacks can be represented using arrays. Stack is a very important data structure and we have also seen that it can be implemented using both arrays